When we think of harmonic analysis, we think of the Fourier series, the Fourier transform. We can also have wavelets. So it is a theory related to representation, a certain representation of functions, but this kind of representation is performed in the frequency domain, quote unquote frequency domain. Now, harmonic analysis can also be performed on groups, and I want to say something about this in this lecture. In particular, let me define a function which depends on R, where R is a certain group. You can think of R, for example, of the rotation group, or you can think of it as the group SU2. SU2 is a group related to 2 by 2 matrices, which are complex matrices, and they are also unitary matrices, so I will not explain the details of SU2 here in this video. I will assume some familiarity with it, but let's say that anyway SU2 is related to rotations. And now we have a function that depends on the group. So by f of r, I mean that f will depend on the parameters of the group. For SU2, for example, you have 3 parameters. In general, the number of parameters is equal to n squared, which is the dimension of the matrix. You have an n by n matrix in SUN. So you have n elements here on the row and n elements here on the column. So you have n squared elements. And then you subtract 1, which is the number of parameters of the group. So in 2 dimensions, for SU2, you have 4 minus 1. That is 3 parameters. And anyway, apart from this, we want to expand this function. And I will write the expansion, and then little by little I will tell you more about the details of the expansion. So we sum over 3 numbers, j and n and also m, and then here I have some coefficients, c, n, m, j, and then I have some matrices that depend on the group. So these are representations of the group d, j, n, m of R, and I will also put a star here to denote the fact that these matrices are complex conjugated, and I will also put another factor 2j plus 1, and I will explain this factor later. But anyway, this is an expansion performed over the set of matrices. This set of matrices D are called the Wigner matrices. These are representations of the group SU2. So in general, you might have other kinds of representations for other groups, but in this case, I'm really focusing on the SU2 group, and I'm going to label the matrices like this. These are called the Wigner matrices, which form they form a complete set. So you can expand a function of the group in terms of these matrices. Now, this is very similar to a Fourier series expansion if you think about it, because here for the Fourier series expansion you have complex exponentials. In this case you have a representation of groups, so it is some kind of generalization of that. And then why are we summing over j over n and over m? Well, because these are matrices, we can think of n and m as the matrix indices. So this might be the row index and this might be the column index. And then we also have another index j, which is related to the spin of the representation. So you might have a representation for spin 1/2, you might have another representation for spin 3, and so on. So j will take all the values which are multiples of half integers. So you also start at 0, then you have 1/2, you have 1, you have 3/2, you have 2, you have 5/2, and so on. So you get the idea. Whereas these numbers, n and m, they are both contained in the interval minus j and j, and they also take half integer values. So n and also m, so this is the same for m, they take 2j plus 1 values, and this is related to this constant, but I will explain this factor later. It's related to the dimension of these matrices. You can see that each of these indices can take 2j plus 1 values. Anyway, now We have a formula for the Fourier series, quote unquote Fourier series. If you want, you can call it generalized Fourier series. You also have a formula. We must have a formula for these coefficients here. And in a similar fashion to the Fourier series, we define the formula in the following manner. So at the moment, we can take this as a definition, and later we'll see if we can be consistent with these definitions. So we have C and M J, and we define it to be an integral over R, and I will have to explain what this dr means in a moment. So we integrate over R over the group, then we have f of R, and then we have the Wigner matrices dj and M of R, and this is indeed C and M of J. Now you can see here that the Wigner matrices are not complex conjugated like in here, so we don't take the star of this. And this is similar to the fact that, for example, when you consider the Fourier series, in the series, you have e to the I something like omega n t, if we consider the variable t, so we would have a function f of t here. Whereas in the integral, we have the complex conjugate of this, so e to the minus I omega n t. And this is the reason why here you have the complex conjugate, and here you have the Wigner matrices. You could also have the opposite, so you might have the star here, but if you put the star here, then there should be no star there. Okay, so this is just some details, and I don't want to focus too much on this now. Now let me explain, let me give you some more details on the integration over R. So what do we mean? Integral over dr. Well, by integral over dr, we mean that we are integrating over the parameters that define the group. So for SU2, this would be an integral over three angles, for example, or three parameters. We have an integral over alpha, over beta, and over gamma, and we might have some normalization constant such that the measure is equal to 1. And indeed, this is what we will do. In particular, we will define the measure such that the integral over the measure gives us 1. And we will see that when we impose this condition, we are forced to consider this factor 2j plus 1. And we will see it in a moment, so in a few minutes. And now let me give you some interesting formulas. In particular, if we consider dj and m, and we set the rotation equal to 0, well, it is quite intuitive that we must obtain the Kronecker delta and m here. Why is that? Well, because we have to think that these Wigner matrices are representations of a rotation, and the rotation depends on R, on the group. But if we choose the group to be 0, in particular, if we choose 0 rotation, then it makes sense to consider the fact that the Wigner matrices will have to be equal to the identity. So these are 2j plus 1 times 2j plus 1 matrices. So we can see that, I mean, it is quite intuitive that we get the Kronecker delta there. Now, I want to use the two formulas above, so in particular this one here and this one here. I want to choose a function. I want to choose f of r equal to delta of r. And in this case, we have to interpret this as the Dirac delta. So if I use this formula here first, I have integral over r, delta of r, then I have d and j of r equal to dj and m of 0. So I'm simply using the properties of the Dirac delta. When I multiply a function by a Dirac delta, I can evaluate the function at the point where the Dirac delta has its peak. So the peak of the Dirac delta is at r equal to 0. Therefore, we get dj and m of 0, which we can factor out of the integral, and then we have an integral of dr delta of r. So the integral over the group of the Dirac delta is equal to 1. So here I can multiply this by 1, which is like considering this simply. And this is equal to delta and m, which in principle also depends on j, if you recall, because n and m can take 2j plus 1 values. So this implicitly depends on j. Anyway, now if I consider this, I can uh, I can define this delta nm to be my coefficient c nm of j, because I have simply used this formula here, right? So in the particular case where, in the special case where the function is equal to the Dirac delta, the coefficients are equal to Kronecker deltas there. And now I can use the formula here. So I have an expansion for the Dirac delta that depends on a group. So delta of R is equal to a sum over J over N over M delta Nm dj Nm of R to J plus 1. But now I can also rewrite this as the trace of dj of R. When I think of dj of R, I am simply omitting these two indices, and I'm using matrix notation where the two indices are hidden, and I can take the trace over these two indices. So this is basically the trace of a matrix where the matrix is defined to be dj of R. Simple as that. And this is an important formula that's also used in loop quantum gravity, for example. So the formula, let me rewrite it because it's an important formula. We can expand the Dirac delta, and this Dirac delta of a group appears in loop quantum gravity. For example, this is just an example. We sum over J here. So we simply have to sum over J because I'm already performing the summation over N and over M here when I consider the trace. So I have the trace of dj of R times 2j plus 1. So this is an important formula. And it generalizes a formula for the Dirac delta in a simpler cases, for example, in the Fourier series representation, where instead of having this trace here, you have the complex exponentials. Anyway, I have not concluded yet. I want to show you something more. In particular, I want to use these two formulas one more time, this one and this one, where we have the generic function f of r. Now, I can take this formula here, and I can put it inside the integral here, inside here. So I can substitute f of r written like this in here. And now let me do it, because as I said, we have to make sure that our formulas are consistent. So when I do that, I get an integral over dr, and then I have a summation over j over n over m. Let me put 2j plus 1 here, and then I have c n m j d n m j of r star, and then here I have d. Let me change the indices here, because here I'm summing over j over n and over m, so I have to change the indices that appear in this formula n, m, and j, because these n, m, and j are different in general from these n, m, and j, because these are dummy indices. We are summing over them, so we have to differentiate the indices there. So I'm going to use j prime, n prime, m prime of r, and then this must be equal to c n prime, m prime, j prime. But now I can perform the integration over R over the group there, and I have to impose the following condition. If you just check the formula that you have above, I will impose the following. So I have integral over dr dj nm of r star dj prime. Then I have n prime m prime of r, and this must be equal to delta n m prime delta m m prime delta j j prime, and we also have to divide by 2j plus 1, because when you integrate this and you get this factor 2j plus 1 will cancel this factor here, And then when you consider these Kronecker deltas, this will make sure that you get this index, this coefficient equal to the coefficient Cj prime, n prime, m prime. So all these Kronecker deltas will make sure that the right coefficient here of this expansion will be equal to the coefficient here. So this is an orthogonality property of Wigner matrices. And you can see that it arises quite naturally once you start from the Fourier series, the generalization of the Fourier series. And it's inverse if you want. So you have, it's like a discrete Fourier transform, if you want. It's not really like that, but just to understand each other. So the Fourier series, if you want, you can think of that as some kind of discrete version of the Fourier transform. And basically, this is what we have been doing. So we have started from two definitions. One definition, which is the definition of the Fourier series, and then this is like taking an inverse. It's some kind of inverse which gives you the coefficients that appear in this expansion. But anyway, now we are close to what I wanted to get to. In particular, as I said earlier, we want to find a measure, we want to define a measure such that when we integrate over the measure, we get 1, right? Now, I want to do a simple trick here. So in particular, we can also rewrite it in the following fashion. So we have an integral over delta over dr, and here I'm going to put a Kronecker delta nh, and this of course must be equal to Kronecker delta nh. But now I can also represent the Kronecker delta in a different fashion here inside the integral. In particular, we have integral over dr. Then I'm going to sum over m, and then I have dj nm of r, and then I have dj mh of r inverse, and this must be equal to delta nh. So here I have basically performed a trick. So what I get from here, from here is basically the matrix dj of r acting on dj of r inverse. Now, this is quite intuitive that when we consider Wigner matrices of a certain rotation and we act on a matrix which is a representation of the inverse, we get the identity. So it is quite intuitive that this should be the case. And another intuitive property is that we are dealing basically with unitary matrices. So the representation of the inverse is equal to the representation of R, and then we take the dagger of that. So this is what it means, that these representations are unitary. Basically, we are imposing the fact that these representations are unitary. So the matrix multiplied by the dagger of the matrix itself gives us the identity. So this is what we are considering here. And basically, I can rewrite it as integral over r sum over m dnm j of r d, and then I have j mh of r dagger equal to delta nh. But now the dagger, if you remember, is just the transpose complex conjugated. So if we transpose this matrix, we get we have to change the order between these two indices. So I have h, and then I have m here, like this, and then I will be left with the star. So I have to take the complex conjugate, because I have taken the transpose, but I also have to take the complex conjugate. Now, at this point, I can integrate over R, and I simply have to remember this property here, right? If I do that, what I get is the following. So I get sum over m from here. Then I have delta nh, delta mm, and I also have delta jj if you want, but I will not write that. That will be 1. Also, this will be 1, but I have rewritten this for the sake of convenience because I have to sum over m, but it's not important. If you want here, you can just put 1 because that is indeed equal to 1. We have to divide by 2j plus 1, and this must be equal to delta nh, right, from there. And is this correct? Well, the answer is yes, this is correct, because when you perform the summation over m, you will get another factor of 2j plus 1, which will cancel this. So you will have 2j plus 1 divided by 2j plus 1 times delta nh equal to delta nh, right? So you get a correct identity there. And that's the reason why we have found, we have considered this factor 2j plus 1 here. This factor gave rise to this factor here in the denominator, and the importance of this factor is due to the fact that we have to impose, so we can impose the integral over r equal to 1. If we impose that, we have just seen that we must consider the factor 2j plus 1 in the above expressions here, because otherwise we would not have gotten the right equality here, right? So that's a factor that must be considered. Now, to conclude this video, I want to compare the expansion over Wigner matrices with the expansions over spherical harmonics. I will tell you more about spherical harmonics in the subsequent section if you are interested. It is just some kind of a reminder of previous lectures and courses, but never mind. So the focus is not on spherical harmonics, but if you are interested, you can check out the subsequent section and discover more about them and the relation between spherical harmonics and the Wigner matrices. But now let me consider a function of the kind f of r omega. I will write it like this. This omega here is a solid angle, and you can interpret this r omega in the following fashion. So we act with the rotation on a certain unit vector that depends on omega. So the unit vector will depend on some angles, and basically we are rotating that. So we are saying that this function depends on a rotated unit vector. Okay, we can expand this function over Wigner matrices. So we have to sum over j over n over m. We have a bunch of coefficients c and m of j, and the coefficients in general will depend on omega, so they will depend on the solid angle, or if you want, the unit vector. And then we have the Wigner matrices that will only depend on the rotation. So we have d, j, and m of r star 2j plus 1. But now we can also expand this function here over spherical harmonics, because now we have a rotated quantity, but in general the quantity will depend on some angles. And when we deal with a function that depends on some angles in this fashion, we can also expand it over spherical harmonics. So we can sum over j over n, for example. Then we have some coefficients a, h, and j, and then we have psi and j, which are the spherical harmonics, and they will depend on the same argument r omega, like this. But now spherical harmonics in general can also be used here in the definition of these coefficients, because these coefficients depend on omega, and since spherical harmonics are a complete set, we can also assume that these coefficients are proportional to some constants a and j, so these constants might depend on n and j, and then we have psi j m of omega. And now if you compare the two formulas there, you can see that psi j n of r omega is proportional to the sum over m dj nm of r star psi j m of omega here. So you can see basically that a rotated spherical harmonic, so you can think of this as a spherical harmonic of a certain rotation, is proportional to the Wigner matrices applied to spherical harmonics which are not rotated. So you can see that Wigner matrices are related to a certain rotation of spherical harmonics to be interpreted in this fashion. Now, I think that I have said a lot of stuff in this video, and I think that it might be enough for now. So, if you are interested in spherical harmonics, you can learn more in the subsequent section.